To begin, we're going to do the analysis of three materials: steel, aluminum, and fused quartz. Import the data into the indent grapher. You can click on the files. There's the aluminum. There's the steel. And then there's the fused silica. To show the difference, you can change the color of each curve by right-clicking on the curve and selecting color. We'll make fused silica blue. Make the line thicker. Then take the steel to make that one green. And then the aluminum. Let's make that one purple. Okay, there's our three sets of data. The standard feature for measuring the elastic modulus, of course, is just click on the curve and then calculate. In this case, the elastic modulus is 50.54, which is lower than expected, but the machine or the indenter could be out of calibration. But that's going to be our baseline for doing the rest of the analysis. What we'd like to do is see how the elastic modulus changes along the curve. Let's say we went from 20 to 50. You could see that the elastic modulus in this lower section is 55.04, and it's 50 at this point. If we do the same thing with the steel sample, it's 199 at this portion, and if we go from 50 to 100% of the curve, it's 178.74 gigapascals. Then let's do the same thing for the aluminum sample. Here it is in the top portion, and here it is from 20 to 50. Calculate. 62.4. What we'd like to do is actually see what the elastic modulus does along each one of these sections without having to click on and enter the section of the curve one by one. To do that, you can use the advanced function. So you just click on Add to Graininess Graph, Elastic Modulus versus Height. And there you go. You can see how the elastic modulus varies along the unloading curve. And as you can see, around 602 nanometers, there seems to be a large elastic modulus, whereas at another portion, at around 591 nanometers, there's a lower elastic modulus. Now let's compare that to, for say, the fused silica. Click on that curve with the left button, go to Advanced, Add to Graininess Graph, and now you can see that material. And as you can see, the aluminum has a larger variation than the fused silica. Let's do the steel sample now. Add it to the graph. So there you go. Now you have the fused silica, aluminum, and steel. So let's say you wanted to add the text to this. So you push the Control T, then you would type in fused silicon. Silica. Okay, type that. And then here's the steel one. Control T, steel. And then there's the aluminum. $50 alloy. And there we go. Now we have a graph that compares the elastic modulus variation along the unloading curve for these three materials. As you can see though, they're spread out along different depths. We could also plot these using the same zero. To do that, start the graph over. Click on it. Click on Advanced. And then before you make the graph, click on Zero Start Depth. What that does is it puts the lowest depth at 0 so that all of the materials can have the same starting point for easier comparison. You can see now it starts from 0 to 87 nanometers, which is, if it was going between this point here all the way up to this point, would be 87.3 nanometers. Now let's add the other materials. Here's the steel. And now let's add the final material, aluminum. Now there we go. Now we can compare these three materials: steel, aluminum, fused silica. If you want to label it, type in steel. This is actually a ferritic steel. You put an F for ferritic. And here's our aluminum. Control T. $50 alloy. And fused silica. Control T. Fused silica. Boom. Alright.